Looking at the electrolyte of the PEMFC, we again have a look at our requirements first. So the requirements for our Nafion is that it has to be a good proton conductor. This means that we can facilitate a high diffusion rate of protons through the electrolyte. This basically just means we can facilitate a fast transport process and also a process which does not give rise to extra resistances within the material. We want our electrolyte to be a bad electron conductor because, of course, we want to electronically insulate the anode from the cathode to prevent short circuits. And by having conduction via the electrolyte, we would have something called an internal short circuit. And of course, all of these internal short circuits might lead to the critical failure or at least the loss of efficiency of our fuel cell. Furthermore, the electrolyte has to have a chemical stability in oxidizing and reducing atmospheres. That's the case because on either side it's in contact with the anode on one side and with the cathode on the other side. So the electrolyte has to be able to withstand both kind of atmospheres and both kind of potentials being exhibited at these electrodes. So this helps us to avoid decay. If you think back about different degradation mechanisms of electrodes, some of them were related to electrolytes as well. So of course we want to keep an intricate contact between the electrolyte and our cathode and our anode in order to provide the possibility for efficient ion transport from the electrode into the electrolyte. Because I've highlighted before that there's a high significance of this triple phase boundary, and this requires that all of the three different phases, the gas phase, your cathode, for example, and your electrolyte, are in spatial proximity to one another. And another pretty obvious point is that the electrolyte has to be gas tight, of course. So what we do not want to have is a crossover of fuel, for example, from the anode side to the cathode side, and thereby losing fuel and also giving rise to possibly parasitic reactions. So all of this would basically lower your fuel efficiency. We've already seen that the typical electrolyte used for such cells is so-called Nafion, so sulfonated polytetrafluoroethylene, which is PTFE. So PTFE is polytetrafluoroethylene, and sulfonated is the special part which makes it pretty much transporting polymer for protons. So again, this kind of main branch here is giving us mechanical stability. This is just extending further and further. That's why it's a polymer. And this proton conduction is ensured by having this sulfonated part. If we now have a closer look at that, at this conduction mechanism, we notice that we have something like a hydrophobic chain here. So we have elements and a construction which is basically rejecting any closeness to water. This part of the molecule here does want to surround itself, not with water, but rather with itself. And on the other hand, we have this other part here, the so-called hydrophilic clusters. These can take up water, or H2O, as it's also shown here. So what can happen if you have multiple of these groups together here is that you basically form a outer region where you just have this long polymer chain everywhere. And these groups here, which of course like continue, like from the next segment here, again, there would be such a group. These groups are all like directed towards each other, and next to them, there can be an accumulation of water. Due to this phenomena, we can now conduct via this vehicle mechanism, which basically works by simply transferring a proton, as you can see it in white here, from one water molecule to another. And this shows us why the proton conductivity is so closely coupled with the water content, because the protons are basically transferred via the water molecules.